guys, we are starting Unit 15, which is reaction rate. Chemically, this is how quickly the number of moles or molecules or particles react in a reaction, the time it takes. Some reactions are very, very quick, almost instantaneous, while others take a while. We measure rate chemically for all kinds of reasons. How quickly is a fuel burning? So in the petroleum industry, that is a big concern, how quickly we burn fuel. It's our metabolic rate that we talk about as far as our cells and how quickly we burn food. Medications are also tested to see how long it takes for them to help or to begin to react within a person's body. It's one of the ways that they get how to dose people. And so it's a big deal. We are just hitting, again, the highlights. This is an introduction, but this is another one of those fields in chemistry that you could make a career out of. Now, as far as factors go that affect rate, we've talked about most of these things before, and so a lot of this information will be repetitive a little bit or a review of the things that we've talked about. But we'll talk about concentration, we will talk about temperature and have those two kind of together, and then talk about catalysts, and finally do the nature of reactants in this first little section on reaction rate. Now, as far as an explanation for why each of those factors affect rate, they call this the collision theory. And in the collision theory, you have two parts. The first is the collision frequency, which is how often do collisions happen. So the number of collisions per time. And two of the factors that I already mentioned have a lot to do with this. The first is concentration, and then the second is temperature. First of all, the first thing to know is that the reason this is studied is that molecules do actually have to come in contact. They must collide with each other before a reaction can occur. And so there has to be some sort of contact. So with concentration, our first factor, why does it affect the rate of reaction? So you guys have seen a picture similar to this in our notes. And so in these particles, or in these containers, excuse me, which particles are going to hit more often? Obviously, I hope you will tell that it is this one, because there are more of them in there. There is a higher concentration in that container. So I always give the example, think about the hallway down in the high school. If it is during class and you ask it to go to your locker to get something, there's a very small chance you will actually run into someone else physically, like touch them, because there's not very many people out there. There may be no one. But if it is between first and second hour and everybody comes out of all of the classrooms that are down there all at once, there is an extremely good chance that you will actually have to touch somebody else in the hallway because you're packed in there. That is high concentration. Now, as far as substances go, if we're talking about a solution, that is measured in molarity. So again, how many moles are in how big a volume. If it is solids, the concentration is determined by the surface area. And so something that has a higher surface area will react faster. And that is the reason that things that are crushed up will dissolve faster or react faster. That's the reason that we, when we talked about making our hot chocolate, that we would crush up the little chunks that didn't dissolve quickly. Increase surface area. And then with gases, very often the concentration of a gas can be determined or closely measured in terms of pressure. The higher the pressure, the more concentration or the more gas molecules that you have in a container. Now, the second thing that affects the number of collisions is temperature. And we have talked a lot about the fact that when molecules are hotter or at a higher temperature, they are moving much, much faster, which means that if they are with other gas molecules that are moving fast, they will have a tendency to collide more often because they are covering more ground or more space more quickly, and they are moving fast, so when they do hit, they hit with more force. If you have this fast-moving molecule and it hits another molecule, it has what is called the proper activation energy. And we'll talk about activation energy in just a minute. but it is really helped by those higher temperatures. And I have that question on there, what happens at lower temperatures? Just the opposite. You have fewer collisions, and not only that, they are hitting with less force. And so the cold temperatures just really will slow the whole thing down. Now, back to activation energy. This goes into the second part of the collision theory, which is collision effectiveness. So this deals with what percentage of the actual collisions do result in a reaction. Not all chemical collisions or molecule collisions produce a reaction because they have to have what is called the activation energy. And the activation energy is the lowest amount of energy that you can have between colliding particles and still have them react. It's represented usually by this, a capital A with a little subscript, a capital E, with a little subscript A, the energy of activation. And on a graph, it is usually represented by kind of a big hill in the middle of your energy graph. You're still starting over here at the reactants. You're still going to end up over here at the products, but you have to get up this big hill before you can kind of roll on down to the products. That hill essentially is the activation energy. Now, with the activation energy, it kind of goes back again to what we said with temperature. If you have differences in your activation energy, it can really make a difference in the time that it takes for the reaction to happen. And so I've got two graphs here, one with a very low activation energy in the first graph, in graph A, and then one with a much higher activation energy in graph B. And I always kind of think about it in terms of, if I have to walk up a hill, how quick am I going to go based on the size of the hill? In my physical state of condition, this little small hill is way more my speed. This one I can get up pretty quickly, and then I would roll on down to the products. If I was over here on this second graph, I would not, oh goodness, I would not be super excited about trying to get all the way that hill. It would take me a long, long time. So if you have a lower activation energy, like you do in that first graph, you have a faster reaction. So the lower the activation energy, the faster or quicker, however you want to put it, the faster the reaction goes. So if you can lower that, you are going to definitely speed up your reaction. Now, which brings us to our next factor that contributes to rate, and that is a catalyst or an inhibitor. They are opposites of each other. We talked about catalysts in terms of enzymes a little bit last year in biology, and an enzyme in your system is something that helps you to break down your food. If you didn't have these enzymes, food would sit in your stomach and in your digestive tract a lot longer. The enzymes act as catalysts, and they lower the activation energy that it takes to digest or to break down the foods. And what they do is they basically are a shortcut. They are a little side road for the reactants to take that will get them to the same ending point, but it will get them there faster. And so you have another chemical basically added in of some sort, and it changes that reaction rate, but it does not become part of the product. It is not consumed. You get it back at the end of the reaction. An inhibitor, oh, and in this graph, sorry, back to the catalyst, the red line, the smaller hill on there, is the activation energy with the catalyst. So again, the lower the activation energy, the faster the reaction. Now, an inhibitor is the opposite of a catalyst, and it raises the activation energy. And so it would take the activation energy on this graph that we have, and it would start at the same point. We'd still start down there where reactants are, but now we'd have this much, much bigger hill that we would have to get up to before we got down to the products. And you use inhibitors probably every day if you put stuff into the refrigerator. An inhibitor, remember, slows everything down. Cold slows down the molecules. So it's not a chemical inhibitor, but it does act as something that slows the reactions. If you put something on, like when you cut apples up and you want to freeze them to make pies later, lots of people will put like fruit fresh on them or Sprite or something like that to keep them from turning brown. That is an inhibitor. So there are different ways to preserve foods. Again, those are all inhibitors. Chemically, we are just stopping or slowing the reaction by raising the activation energy way above where it should be. Eventually it's going to come down. Eventually your apples are going to turn brown. Eventually your milk is going to go bad, even though it's in the refrigerator. But it is much slower than if you just left it without. Last thing for today, the nature of the reactant. So this is the last thing that is going to affect the rate of the reaction, how quickly it will react. And that depends on what is actually reacting, what the reactants are. And there are three main groups that I want to mention that are more active. This is really similar to some of the periodic trends that we talked about, like with Big Frank and Pretty Flow and all those things. It's kind of those same elements or those same areas. The more active metals are the bottom left of the periodic table. So there's our good buddy Big Frank again, Big Frank. And anything that is close to him is going to have a faster reaction rate than something that is farther away. So if I were to ever ask you what's going to have a faster reaction rate, and I was asking you to compare something like, sorry, I don't have a periodic table from it. If they were comparing something like calcium versus cobalt, calcium is much closer to Fr, so it's going to react faster. Same thing on the other side or the opposite side of the periodic table. More active nonmetals. Remember, this is not going to include those noble gases. Remember, they're noble. They don't want to react with anything else. But more active nonmetals. So this is Pretty Flow over here. That is, so again, whatever's closest to F is going to react faster than whatever is farthest from F. And then the last one, a strong acid or a strong base. Remember, when we talk about strong or weak in this situation, we're talking about how well it dissolves. A strong acid will dissolve 100% in water or dissociate 100%. It will have a higher activation, a higher rate of reaction than something that is weak because it has more particles in the solution. It basically has a higher concentration. Okay, so those are the four factors that affect the rate of reaction. Let me know if you guys have questions.